Hi to everybody, I'm Marco Di Giovanni, and I will talk about finding multiple solutions of ordinary differential equations with neural networks. This work has been done with my supervisor, Marco Brambilla, and David Sondak and Pavlos Protopapas from Harvard. Okay, slide. So I will briefly introduce the topic. I will talk a bit about ODEs, like the notation, just to be on the same page, and how to solve ODEs with neural networks. Then I will briefly present the equation library, so the equations that I decided to use as a test for the algorithm. I will describe the methodology of the whole process, and then I will present the results with some discussion of the selection of hyperparameters that has been done and that they are introduced in the algorithm. So as you already know, in physics, there are a lot of examples here. I just put two just for reference of differential equations, ordinary and partial of any kind, from fluid dynamics with Navier-Stokes equation, quantum mechanics, but many more of them. And there are, of course, classical methods to solve them, and now the community is giving much interest in solving differential equation with neural networks. But the idea of this work is that not all the differential equations have just one solution, but there can be samples of many solutions, and we want to find all of them. And since neural networks now have some advantages with respect to classical methods, the idea of this work is to build an algorithm to find all of them without knowing the number of solutions. Okay, so some notation here. I have an ordinary differential equation that we can write as a function of an independent variable t and the u of t that will be the solution, the function to find, and its derivatives. Now, t can be more than one-dimensional, but in this work, just to test the algorithm, we decided to just stay with one-dimensional problems in an interval, a fixed interval that it's called T0, Tf. And okay, and the goal is to find the function that we call u of t. We decided to test both problems of initial condition and boundary value problems. So initial condition problems that we define fixing all the values of the function and its derivatives at an initial point. And an example can be, for example, SIR model with the definition of susceptible, infected, and recovered percentage and their dynamics in time, or boundary value problems that can be the eighth equation where we know the value of the function at the extremes. In this case, since we are one-dimensional, just T0 and Tf, and we want to understand the function in the interval. Okay, and some classical methods that solve this kind of problems are Runge-Kutta, for example, where we discretize the space, used usually for initial condition problems, where we discretize the space, start from the beginning, where we have T0, and then iteratively approximate the function. I have just an example of a fourth order Runge-Kutta, and where, of course, we approximate the function iteratively in all the points that in the interval, let's say. While for boundary values problems, for example, we have finite differences where we still discretize the space and we approximate the derivatives. In this example, is just one dimension, one first order approximation, and then the only thing that we have to do is to solve a linear problem. As you can see, there are different ways to solve both of these problems. One of the main advantages of neural network is that it can solve both of the problems without major modification on the algorithm. And these and many other advantages that are described like better in some original papers, give the idea that maybe trying to apply this method of finding all the all the solution can be a good idea to apply with neural networks. So like the brief theoretical idea on why to use neural network is the universal approximator theorem, where it basically states that even a single hidden layer feed-forward neural network can approximate any continuous function. So we are working with continuous functions if the with an error related basically on the number of neurons in the hidden layer. This is theoretical. We will use larger networks, but still give an idea of why to use neural network. And how do we solve that? The idea is quite simple. We use the neural network as the solution of the differential equation, where in this case we have k hidden layers with h neurons per layer. And what we have to do is just to learn the parameters of the neural network, and then given a neural u of t, we can easily calculate the derivatives that we need, and then we can compute the loss function that here is just the square of f. And when we minimize this, it means that the differential equation is solved. So that's our goal. And how to calculate the derivatives? We use Autocrat that was firstly introduced to calculate the derivatives with respect to the parameters of the neural network. Here we also use this to calculate the derivatives with respect to the input, that in this case is one-dimensional, so we can calculate all the derivatives and applying Autocrat to the derivative and so on, until at least the ones that we need to calculate the loss. But in
just a quick question on Autocrat. So what? What do you mean? It's what does Autocrat do, and what do you mean by it's different from both numerical and symbolic differentiations?
Okay, basically Autocrat is not. What it's doing is to create during the computation of like the definition of the neural network, another graph that basically saves the derivatives and of every step. So this is not an approximation like numerical methods that usually approximate the derivatives, nor symbolic differentiation that actually calculates the analytical expression of the derivatives. Is this new
but you mean it's automatic differentiation? It's automatic differentiation.
Yeah.
I see. Okay,
and we apply that, not just to calculate the derivatives with respect, like for training the parameters, but also to calculate at least, of course, the derivative of u with respect to the input parameter, that it's not being done in classical neural networks.
And you do this, so but basically you're not using TensorFlow and gradient in TensorFlow, you're just using this, you're implementing the neural network in a separate software and then using Autocrat to differentiate.
Actually, I use the implementation in both TensorFlow and PyTorch. In this paper, I'm using PyTorch, but it's the same implementation that PyTorch uses to calculate the derivatives with respect to the parameters of the neural network.
But then why do you use Autocrat? I mean, you can just differentiate with PyTorch or TensorFlow.
I think it's basically the same thing. I use Autocrat because it's probably faster, or it actually has already computed the graph of the derivatives with respect to the parameters. So this is just adding a new leaf when where we have like the number of leaves as the number of parameters.
Okay, thank you, Ian. Thanks.
Okay, and what we need is also to enforce initial condition or boundary values, because in the loss defined earlier, there's no information of this. There are two methods in literature. One that is creating another function. In this case, I call it u hat of t, and enforcing them perfectly. So for any choice of parameters of the neural network theta, the new function u hat of t satisfy the initial condition. Here there is an example of the simple one. but it can be defined for any kind of initial condition. But in this paper, we actually tested that, empirically tested that the other method that I call here method 2 is giving better results, where we define a new loss without redefining the U. And this loss is the one defined earlier plus a new term that with a weight, and the difference of the values of the neural network at the calculated at the initial condition or the boundary values minus the fixed value. So in this case, we are not perfectly satisfying the initial condition, but still minimizing the loss we need. We find that the final error is lower than the first method. Okay. Okay. Here, since we want to test an algorithm to find all the possible solutions, I decided to test two different equations. The first one is Clairaut equation. You can see the general form here. It's an initial condition problem, so we know the values at t0. And there are two classes of solution, a parametrical one and a linear one. So we decided to test two cases with a different definition of f and a differential initial conditions, so that for the first case we have two solutions, while for the second case we have three solutions. So to test both if it works with 2-3 solutions, the algorithm. And also we decided to test a boundary value problem. In this case, we decided one-dimensional Barato problem. The general form is written there, and we know that there are two solutions if the parameter C is less than a threshold value. So we set C less than 3.5, in this case 1, and we have two solutions. The analytical form is known both for Clairaut equation and Barato problem, because we want to test it to test the algorithm, and we want to understand if it's working or not. But in principle, it can be applied to all the all different, like even if we don't know the analytical solution. So the main idea is, since we want more than one solution, we will define more than one neural network, all of them calculating a different solution, and we must be sure that they are not converging to the same solution. So the first thing that we define is an interaction function.
Sorry, I just have a quick question again. So when you mean different solution, you mean because of use different initial conditions, or you change parameters in the ODE? Where are the different solutions coming from?
For example, in this Clairaut equation, we have when in case 1, if we define f in this way with these initial conditions, so the same equation, there are two analytical solutions. One that is a parabolic one, 2 times square root of t, and then a linear one that I call here u1 and u2 of t.
Oh, you mean because there's a non-unique solution?
There is a non-unique solution, yeah, and we want to find all of them.
Oh, I see. Sorry, didn't.
Okay.
I see. Didn't get that.
Don't worry.
Okay. Yeah, thank you.
Okay, so we train more than one neural network, and we want to be sure not to convert to the same minima, to the same solutions. So we define an interaction function. In this case, we picked up a power of the difference of the solutions. In this case, we plot just a couple of different values of the exponent, just to understand how it works. And we define this for each couple of solutions. So if we are trying to get 3 solutions, we will calculate this interaction function for u1, u2, u1, u3, and u2, u3. And we add these terms with a parameter that we call lambda, the strength of the interaction, to the loss. So we have a different loss that is now the sum of 3 terms: the solution of the differential equation, the enforcing of the initial condition or boundary values, and now the interaction term. Okay.
So another quick question. So you're assuming you know ahead of time how many solutions there are.
No, I'm not assuming how many solutions there are. It will be clear a bit later when I have the full algorithm complete. These are just terms that I'm introducing.
Okay.
Now, yeah, okay. And then the training process will be divided in 3 phases, because actually what will be the result of minimizing the loss function that I defined here is not a function or more than one function that solves the differential equation, because there is this term that actually is like creating a function different from the one that we want. So we define a first training phase without the new term in the loss function. Then we will add it in the second phase, and the last one, the third phase, it will be without the term. And this because what will happen is that at the beginning they will probably try to converge to the same minima. Then in the second phase they will separate from each other and try to be still near the minima but far from each other. So and then in the third phase they will converge, and probably if the strength of the interaction is high enough, they will converge to different minima. Another problem that could arise is that since all the solution will have some fixed points, for example, the initial condition in the initial condition problems or the boundaries in the boundary value problems, we are defining a scaling factor that scales the interactions. So near the fixed points, for example, in initial condition problems near t0, the interaction function will have 0 value, while it will have the maximum value, in this case 1, at the other extreme of the interval. And something similar for boundary value problems with 0 at the boundaries and the maximum in the middle. This is just a linear, but it could be like investigated better. And last, we define a distance. So we want to evaluate if 2 of the solutions are actually the same. And so we define a simple difference, absolute difference of the solution, calculating in the training points, so that we can define a threshold of distance. If the distance of 2 solutions is lower than the threshold, then we consider the function the same, that converges to the same solution, because actually they can converge to the same solution even if the parameters of the networks are quite different from each other. And so this is the way that we define it. And the full algorithm is this one. So as you can see, we first set the parameters, the hyperparameters of the that we need, and then we start with a value of the strength. We create at the beginning just one neural network and we train it. If the loss is lower than a threshold of the loss, then we can be sure that it converges. And so we can okay, we're sure that it converges. So we have no more than one function, so we don't have a distance because we have just one solution. And we can then try to test if there are 2 solutions. So we redo the algorithm, creating 2 neural networks, train both of them, check if the loss is less than a threshold value. If it is, then we calculate the distance between the 2 functions. And then if the distance is less than a threshold that we defined before, then we increase the strength and we do that again. And so on until we reach a maximum value of the strength. That means that even if they are 2 apart, they will converge to the same minima. And then basically means that it's the problem has just one solution. Otherwise, if they converge to different minima, so the distance is okay, then we try augmenting the number of neural networks. So we try with 3 neural networks, we train all of them, we check the losses and we check the distances and so on until the strength is too high. That basically it means that that number of solution is the maximum one that we can reach and no more than that. Okay.
Sorry, can you remind me what is this lambda here? I forgot.
Lambda is the parameter that I defined here in the interaction function, a strength of the interaction function. So basically, the importance of the interaction function with respect to the other terms of the loss, like the solution of the differential equation and the enforcing on of the initial conditions. So the higher
this is
lambda, the more
yeah.
they will be separate, and it will be important that they are separate and not that they will solve the initial condition, but it will be just for a number of epochs in the middle of, in the second training phase.
But and in your, can you show the algorithm again?
Yep.
So
the training phase.
It seems like you're changing lambda all the time. So is this critical in the algorithm?
I'm changing lambda only if they converge to the same minima. So only if there are at least two of the function that we are training that are not distant enough one from each other.
I see. Okay, thank you.
Otherwise, I increase the number and I try to obtain 4, 5, and 6 solutions. So, is it clear?
Yeah. Okay, thanks. Yeah.
Okay.
Hello, this is Lulu. Yeah, from Bronx. So what is K here?
K is just a parameter. It's an fixed hyperparameter that is the increasing of lambda. I will talk a bit later. I will we fix it to 2 just to double the interaction strength at each epoch, at each iteration. Sorry.
Okay, and how do you choose the value of the threshold and for example, the K? The threshold for test whether the solution is a solution, whether the network is a solution.
Sorry, can you repeat?
So how do you choose the threshold for testing whether the network is a solution?
So
how do you choose the loss M, for example?
Okay. Yes, the loss M, basically, it's just value of the loss. Okay, it's a value of the loss that we say that if the loss of the neural network is less than that threshold value, it means that the differential equation is satisfied, because the loss actually is this term here. So if the loss is less than, and then I will tell, for this experiment, I picked the 10 to the minus 4. So if it's less than that, it means that the sum of the f is near to 0, and since f is defined, it's the differential equation. It means that we solve the differential equation.
Yeah. So my question is, how do you choose the value of this loss M? So it's 10 to the minus 3 or 10 to the minus.
Okay. Yes, we decided to pick 10 to the minus 4 because we could check that in some simple cases in other works, with just trying to train at one neural network, that loss basically meant that the function, the error, so the difference between the points and not the loss, between the real function and the found function, it was low enough. So we decided that that value of the loss basically gave enough precision in the function, in the solution itself.
Okay, thank you.
Okay, so the architecture that we picked for these experiments is 2 fully connected layers with 8 units per layer, sigmoid activation function with also skip connections, because we tested and it was easier to find the solution, faster the training, let's say, and with Adam optimizer with some almost default parameters, hyperparameters. And the results are those. So we have a an MSE error on 10,000 test points equally spaced in the domains. And the errors for all three experiments was about 10 to the minus 5. So basically, we cannot see the difference in these plots, the plots of clear equation with 2 and 3 solutions, and the plot on one-dimensional Berth problem. They overlap perfectly. And so the algorithm works quite fine for these simple problems. The selection of hyperparameters, it's quite simple. Let's say the strength hyperparameters, so lambda 0, k, and lambda m are the initial strength, the strength increase, and the maximum strength. We pick the value that you can see, and we tested some of other values, and basically the output doesn't change too much because if initial strength is too low, it will take more time to obtain the solution. If the maximum strength is too high, it will have more iteration before like finding that all the possible solutions are just 2 or 3 depending on the problem. But these hyperparameters doesn't impact too much on the quantitative results, just on the length of the algorithm, on the computational time of the algorithm. While also the maximum loss is quite intuitive. The lower the better, of course, but we saw that a parameter and value of 10 to the minus 4, it gives good result for the MSE. While the threshold on the distance is the parameter a bit more trickier, because if we define it too small, it means that basically there are 2 solutions that there could be 2 solutions that are distant enough because their distance is higher than dm, that in this case we picked it too small, that even the clear equation with the first case, so with 2 solution, gives results as the one in picture, where we find at least 3 solutions, and then if we run it more than this, also more than 3. So this is the trickier parameter, and basically knowing the range of the function, it helps a lot to understand how to tune it. So to conclude, in this work, we designed an algorithm to find all the possible solutions of differential equation, and with the methods of neural networks. And we tested it on 3 ordinary differential equations with both initial condition and boundary value problems with 2 or 3 solutions. And we analyzed a bit and described the hyperparameters just to get an intuition of them. And this is, of course, a preliminary analysis, and future investigation will deal with a different, like a study on architecture. So this is a fixed one because we noticed that it is able to approximate the solution that we needed, but also dynamical systems such as ResNet could be interesting to implement and trying to understand if the algorithm still works with these kind of structures. And also testing higher dimensional ordinary differential equations, also PDEs or systems of ODEs, to test if the algorithm still works. But since the algorithm is not theoretically dependent on these characteristics, it should for our intuition. Thank you.
Okay, yeah, thank you very much for your presentation. Yeah, very interesting. So I just have a quick question. So what did you test your algorithm on cases where there's an infinite number of solutions? I mean, for some cases, you know, you may have an infinite number of solutions. Did you look at that, or?
No, I didn't, because actually usually when you have an infinite number of solutions, they are a continuous range, so they are near each other for some ranges, and this will not work because we defined a threshold on the distance. So if they are a continuous range of solutions, basically just changing a parameter usually, it will not work because of how it is like built, the algorithm.
I don't get that. It will not work in what sense? I mean, of course, the
usually,
solutions might be, for example, equal for some time at the beginning, but at some point they're going to become different.
Okay, I've not tested those cases. What I try to test, it was the like solutions that are basically an analytic form with a parameter that for any value of the parameter, that is a solution of a differential equation. And in that case, it will not work because the family of solution like is continuous with respect to that parameter, and so the solution will be near each other. At least there will be one solution near the others, at least in our range.
So you mean you're going to be, the distance will be smaller than dm?
The distance will be smaller than dm, yeah, because it's actually a continuous. So yeah, you cannot define a dm low enough, let's say.
But presumably, okay. Yeah, sure, Caroline.
Yeah, go ahead.
No, I just wanted to say, yeah, I mean, you may not find all the solutions, but the point is, if you take a small dm, you will find many solutions.
Yeah, yes, you will find many solutions. That's true. You will not find all of them because, like, if you have infinite solution, you will have to actually for how is it build the algorithm, create an infinite number of neural networks, and it will at some point explode. But yeah.
No, of course, yeah, okay. Okay, thanks. Yeah, Carla, you
want to I have a question. When you say the multiple solutions of the ODE, do you mean that you have the same initial condition, and then you get several solutions to the ODE, or you start from different initial conditions?
No, it's the same initial condition. So like you can see in case 1 or case 2, let's say case 1, you have the initial condition that is u of 1 equal to. And for this one, you have still two solutions, u1 and u2.
Is that related to the bifurcation?
No, it's not related to bifurcation.
Oh, okay. Okay, I see. Oh, thank you.
Thank you.
Yeah, I don't remember my ODE classes, but basically there are some conditions for uniqueness of solutions that are not satisfied. Essentially, the f function is not differentiable and things like that. Yeah.
Yep.
Yeah.
Exactly.